Conceptual link between VMT and TDA. Why physics-based energy model and geometry-based topology model produce similar biomedical results. Number 1410, VMT sharp 738, TDA sharp 021, October 29, 2025. Gerald C. EclaireMD Foundation. Category, Methodology. Preface. Since 2010, I have self-studied and researched biomedicine, mortality diseases, and general health topics without any funding, institutional support, professors, classmates, associates, colleagues, students, or patients. Starting in 2017, I wrote my first medical research paper on type 2 diabetes management, which was published and presented at the biannual IDF International Diabetes Forum Conference, held from December 5 to 10, 2017, in Abu Dhabi, UAE. Since then, up to October 29, 2025, I have written and published a total of 1,410 medical research papers covering approximately 50 organ-related diseases, with a primary focus on metabolic disorder-induced mortality conditions. In addition, I have delivered around 300 speeches at medical symposiums and conferences worldwide, serving as a keynote speaker in about 80% of them. My first 650 papers were developed using fundamental knowledge from mathematics, physics, engineering, and pathophysiology. Later, I wrote 738 papers, based on the energy models of my Viscoplastic Medicine Theory, VMT. After my recent stroke incident, I began applying both the geometric model from topology theory, 31 papers, and the stochastic model from statistics, 1 paper, resulting in 22 new medical research papers. My personal health journey began in 1985 with obesity, followed by type 2 diabetes in 1990. Over time, I developed hypertension, dyslipidemia, 5 cardiovascular episodes, diabetic retinopathy, neuropathy, including foot ulcers, chronic kidney disease, and, most recently, on June 21, 2025, a hemorrhagic stroke, accompanied by multiple seizures. Except for dementia and cancer, I have experienced nearly all major mortality-related diseases firsthand. In other words, I am not a traditionally trained medical doctor, but a self-learned and self-trained medical researcher, who has spent more than 80,000 hours studying and reading over 10,000 published medical papers and scientific literatures. In short, I am both a serious scientist and a critical patient. My brain serves as both teacher and student, while my body functions as my only living laboratory. In this particular paper, I discuss, from a conceptual perspective, the similarity and applicability of both the VMT model and the TDA model. Introduction. Over the past decade, I have used two very different analytical tools to study chronic diseases and systemic health conditions: the Viscoplastic Medicine Theory, VMT, and Topological Data Analysis, TDA. At first glance, these two frameworks belong to completely separate scientific domains. VMT is rooted in physics and material mechanics and is used in advanced engineering analysis and design, while TDA arises from geometry and topology. Yet, when applied to the same biomedical dataset of output, strain and multiple input stressors, their results consistently show strong similarity. This article explains why their outcomes align so well, even though one is energy-based from physics and the other is geometry-based from mathematics. 1. The foundation of VMT: stress, strain, and energy. VMT originates from classical mechanics. Stress represents the external force or pressure applied to a system, in my case, the biological system, while strain describes its deformation, output, or physiological response. The product of stress and strain defines the system's internal energy. In my model, cumulative, viscoplastic energy reflects the total metabolic load or damage. A higher energy state means the body is under heavy internal tension, while a lower energy state represents improved homeostasis. Each input stressor, for example, glucose level, blood pressure, visceral fat, or sleep hours, contributes a specific percentage of total system energy. These VMT energy contribution ratios quantify how much each stressor influences overall health. When plotted over time, the total VMT energy trajectory shows whether the system is improving or deteriorating. 2. The structure of TDA: geometry, connectivity, and volume. TDA, on the other hand, comes from geometry and topology. Instead of directly computing physical energy, it studies how multidimensional data points connect and form shapes in geometric space. Principal component analysis, PCA, is often used inside TDA to define orthogonal axes. PC1 shows the primary direction of variation, the dominant, behavioral or metabolic trend. PC2 represents secondary balancing patterns. PC3 captures minor fluctuations or short-term adjustments. The resulting geometric structure has measurable features, area in 2 dimensions, and volume in 3. A large area or volume indicates a dispersed, unstable system, while contraction toward a smaller, denser shape, such as a sheet or sphere. Reflects stabilization and lower internal variability. 3. Eigenvectors, eigenvalues, and energy modes. Both physics and geometry rely on the same mathematical foundation. Eigendecomposition. In mathematics, an eigenvector defines the natural direction in which a system changes, while an eigenvalue defines how strongly it changes along that direction. This relationship is expressed as x is lambda x, where A is a transformation matrix, x is the eigenvector, and lambda is the eigenvalue. In mechanical physics, the same concept appears as the principal stress and strain axes, where the magnitude of deformation energy corresponds to the eigenvalue. Eigenvalues do not correspond one-to-one with input stressors but instead describe the combined system response, resulting from all stressors acting together. Therefore, eigendecomposition in mathematics and stress-strain interaction in physics describe the same underlying concept, how a system distributes energy across its natural modes of response. In TDA or PCA, eigenvectors define the principal geometric directions of variance, while eigenvalues quantify the intensity or energy along those directions. In VMT, the strain rate describes both the direction and speed of internal deformation within a material or biological system. Thus, eigenvectors and eigenvalues in TDA are conceptually equivalent to stress, direction and strain rate in VMT. Both describe how a complex system behaves under its natural modes of variation and energy exchange. Since I have already identified that strain rate is the most important indicator in my VMT analysis, by direct conceptual equivalence, the eigenvalue is indeed the most important indicator in my TDA analysis. 4. Mapping between PCA and VMT energy ratios. The relationship between PCA and VMT can be summarized as follows. PC1 corresponds to the dominant stress energy mode, equivalent to the stressor, contributing the largest share of viscoplastic energy. PC2 corresponds to the secondary balancing mode, representing another important but compensating stressor. PC3 represents smaller fluctuations, similar to minor residual energy contributions in VMT. Thus, PCA decomposes total variance geometrically, while VMT decomposes total energy physically. Both quantify how the system behaves along its independent modes. The mathematical structure behind both is identical. Orthogonal decomposition of multidimensional behavior. 5. Area or volume in TDA as VMT energy equivalent. In TDA diagrams, the area, 2D, or volume, 3D, of data clusters corresponds conceptually to the total VMT energy during each time period. A larger area or volume means the system is more dispersed and unstable, similar to high cumulative energy in VMT, when the TDA structure contracts over time, moving from the upper right toward the lower left region in the TDA model. It represents the same process as energy reduction from a high energy state to a low energy state in the VMT model. The system is losing internal tension and becoming more stable. In other words, geometric contraction in TDA is the spatial reflection of energy dissipation in VMT. Both describe disease recovery, health optimization, and stabilization of systemic performance. 6. Unified interpretation. Although VMT uses physics-based energy integration and TDA uses geometry-based topological mapping, both capture the same underlying structure of complex biological systems. VMT measures which and how much energy is stored or released through multiple input stressors. TDA demonstrates where and how much that energy is distributed and reorganized in multidimensional space. When a patient improves metabolically, both methods reveal two parallel patterns, one representing the engineering outcome and the other the geometric outcome. 1. Lower VMT energy at each time period, along with a decline in cumulative VMT energy. 2. Smaller, more compact TDA clusters, moving toward equilibrium regions, with shorter distances among data points. Furthermore, I have described before that strain rate is the key indicator in VMT, because it quantifies the direction and speed of deformation. Eigenvalue is the key indicator in TDA, because it quantifies the magnitude of dominant geometric variation. This one-to-one conceptual bridge demonstrates a complete structural understanding of both models. Overall, this consistent pattern shows that VMT and TDA describe the same biomedical process from complementary perspectives. One quantitative and physical, the other geometric and structural. Conclusion: the reason VMT and TDA yield similar biomedical results is that both follow the same scientific principle. Every complex system operates through natural modes defined by direction, magnitude, and interaction energy. VMT expresses these relationships in physical energy units, while TDA expresses them through geometric shapes, eigenvalues, and topological structures. These agreements confirm that human physiology and disease pathology, like all dynamic systems, obey universal principles of physical energy modeling, including viscoplasticity, and mathematical geometry modeling, including topology. Whether viewed through the physics of stress and strain or the geometry of scale, size, and multidimensional connectivity, the conclusion remains the same: stability, health, and longevity emerge from energy balance, geometric order, and systemic harmony. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only, and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article, and its related materials belong to the author, Gerald C.